This is the last main video in the series where we'll talk about representations of Lie groups and Lie algebras. In this video, we're going to talk about the representation theory of SL2C, which is the double cover of the Lorentz group. In the last few videos, we studied representations of rotations in 3D space. The standard 3x3 rotation matrices that rotate 3D vectors are the SO3 matrices. These can be generated by generator matrices in the SO3 Lie algebra if we exponentiate them multiplied by an angle. The SO3 generators follow these commutation relations. An alternative way to do 3D rotations is to write the XYZ components as a 2x2 Pauli vector, and rotate them using a pair of SU2 matrices. An individual SU2 matrix will rotate a two-component object called a Pauli spinor, and SU2 Lie group matrices have their own 2x2 generators in the Lie algebra SU2. These generators are from the SU2 Lie algebra, and they obey the same commutation relations as SO3. These sets of rotation matrices of different sizes are called representations of the Lie group SU2, and their generators are representations of the Lie algebra SU2. In previous videos, we found that there was one representation of SU2 per dimension n, which can also be labeled by the spin number j, which equals the dimension minus 1 divided by 2. Now we want to move to space-time, where Lorentz transformations keep the space-time metric constant. The standard 4x4 Lorentz transformation matrices that transform 4D space-time vectors form the Lorentz group SO plus 1, 3. These involve 3 rotations, one for each spatial plane, and 3 boosts for changing inertial frames, one for each spatial direction. These 4x4 Lorentz transformation matrices can be generated using these 6 generators, from the Lie algebra SO plus 1, 3. The rotation generators are labeled by J, with 2 subscripts that indicate the plane of rotation. The boost generators are labeled by K, with 1 time subscript and 1 space subscript indicating the boost direction. Sometimes these generators are all labeled by the same letter, like M or S, since the subscripts make it clear what they generate. It's also common to label rotation generators with a single index for the axis they rotate around, and label boost generators with a single index for the direction they boost in. These generators from the Lorentz algebra obey these commutation relations. One thing I was not very clear about in previous videos is that boost generators can have either a plus sign or a minus sign in front of them. Both versions satisfy the expected commutation relations for the Lorentz algebra. We can move from one sign convention to the other just by doing a change of coordinates where we reverse the signs of the XYZ coordinates. This is like reflecting the universe in a kind of 3-dimensional mirror. This change of coordinates leaves rotations unchanged, since reversing both directions in a plane does not change the direction of rotation. But this will reverse the direction of boosts. This applies for both the boost generators in the Lie algebra and the boost matrices in the Lie group, which will boost in opposite directions. An alternative way to do Lorentz transformations is to write the time XYZ components as a 2x2 Weil vector and transform them using a pair of SL2C matrices. These are the 6 Lorentz transformations on 4D spacetime vectors written as double-sided SL2C transformations. An individual SL2C matrix will Lorentz transform a Weil spinor. And here are the SL2C generators. These sets of matrices are representations of the Lie group SL2C, and their generators are representations of the Lie algebra SL2C. Now before, with the matrices that transformed vectors, we saw that boost generators could have either plus signs or minus signs, but we could swap between them using a change of vector coordinates. So these are equivalent matrix representations of the Lorentz algebra. With the matrices that transform spinors, the boost generators can also have either plus signs or minus signs in front. The commutation relations work in both cases. However, we cannot swap between the two cases using a change of spinor basis. So the generators with negative boosts and positive boosts are actually from two different matrix representations of the Lorentz algebra, called the left chiral and right chiral spin 1/2 representations. The rotations are the same, but the boosts are reversed. This applies to the Lie algebra as well as the Lie group. The fact that these left and right representations exist is related to the fact that the irreducible representations of SL2C are labeled by two spin values. So we end up with a two-dimensional table of irreducible representations with all possible pairs of spin values. One consequence of this is that there are two types of spinors in space-time, left chiral spinors and right chiral spinors, but there are many other irreducible representations as well. For the rest of this video, we're going to explain how to get this table of SL2C representations and talk about how some of the representations relate to objects in physics, like four vectors, the electromagnetic tensor, and the metric tensor. So in SL2C, we have 6 generators, 3 rotation generators denoted by J's, and 3 boost generators denoted by K's. Here I'm using the notation where the J index gives the rotation axis, and the K index gives the boost direction. The commutator of 2 rotation generators gives a rotation generator. The commutator of 2 boost generators gives a rotation generator. And the commutator of a rotation and a boost generator gives a boost generator. All other commutators not listed here go to 0. We can take these 6 basis generators and change basis by defining the A's, which are a rotation generator plus I times the corresponding boost generator, divided by 2. We can define the B's in the same way, but with the signs in front of the boost generators changed to be negative. Note that since we're allowing complex coefficients in these linear combinations, we've actually switched to the complexified version of the SL2C Lie algebra, which is denoted with this subscript C. In this new basis, the A's follow these commutation relations, the B's follow these commutation relations, and the A's and B's commute with each other. So in this basis, the commutators split nicely into 2 separate families. Each of these 2 families is equivalent to an SU2 Lie algebra, because these are the same commutation relations seen with SU2. As seen in video 18, whenever we have an SU2 Lie algebra, we can change basis to get a raising operator, a lowering operator, and an eigenvalue operator, according to these definitions. Since these definitions involve complex numbers, these operators belong to complexified SU2 Lie algebras. This change of basis from the J's and K's to the A's and B's means the complexified SL2C Lie algebra is equivalent to the direct sum of 2 complexified SU2 Lie algebras. If we have a Lorentz transformation L from the group SL2C, we can write the Lorentz transformation L as an exponential of the generators in the SL2C Lie algebra. So we have a linear combination containing the J rotation generators multiplied by circular angles, and the K boost generators multiplied by hyperbolic angles. We can also write this linear combination using the notation where the J and K generators only have one index. We can change this basis to the A's and B's as I showed earlier, where each generator gets its own coefficient beside it. Since this change of basis involves complex coefficients, we're now in the complexified SL2C algebra. we can now change basis once again to the ladder and eigenvalue operators. And each of these are a complexified SU2 algebra. So here we can clearly see that the complexified SL2C algebra is equivalent to the direct sum of a pair of complexified SU2 algebras. This is made obvious when we do this simple change of basis. Now, recall that if Lie group members x and y commute, then we can use the property where the exponential of a sum becomes the product of exponentials. So if we take the exponential of a linear combination of our SL2C generators, since the A and B generators commute with each other, we can rewrite this as a product of two exponentials, one containing the A copies of SU2 generators, and the other containing the B copies of SU2 generators. What this means is we can always write a complexified SL2C group member L as the product of two Lie group elements UA and UB, which are each generated from complexified SU2s. Because their generators commute, the A and B group members also commute with each other. So if we have two Lorentz matrices L1 and L2, we can decompose each of them into a product of UAs and UBs. If we compose the Ls, because the A and B versions of the U's commute with each other, we can swap these elements and end up with a product of UAs times a product of UBs. So we can write a complexified Lorentz group element as an ordered pair of complexified SU2 group elements. And when multiplying group elements together, the A elements and B elements just slide past each other and multiply with themselves. Because of this, we say the complexified Lorentz group can be written as the direct product of complexified SU2 subgroups. This direct product symbol indicates members from the two subgroups are written as ordered pairs, where the left elements multiply with left elements and right elements multiply with right elements. Incidentally, this is exactly the property that the tensor product follows when we compose a pair of tensor product elements together. So far we've been discussing the abstract properties of the Lorentz group and Lorentz algebra. But now I'd like to talk about their matrix representations. A matrix representation ρ of the complexified Lorentz group will map every group element to an invertible n by n matrix. Since the group elements can be decomposed into a product, we can also decompose the matrix representation into a tensor product of a left representation ρl for the A elements, and a right representation ρr for the B elements. And remember, to get the generator of a tensor product of group matrices, we take the derivative using product rule, then set the parameter to 0. And we get this formula here with the sum of two tensor products involving generator matrices. So a Lie algebra representation π will map complexified SL2C generators to n by n matrices. As we saw, if we have a tensor product representation, we can take the generators of the various algebra elements and represent them using this formula. Okay, so I realize we've been dealing with a lot of abstract math, and we'll get to examples soon, but let's sum up everything we've learned. The complexified Lorentz algebra can be broken up into the direct sum of a pair of complexified SU2 algebras that commute with each other. As a result, the complexified Lorentz group elements can be written as the product of a pair of complexified SU2 group elements. As a result, matrix representations of the Lorentz group can be written as the tensor product of two complexified SU2 group representations, called the left and right representations. And Lorentz algebra representations are given by this formula. So in order to get an irreducible representation of the Lorentz algebra, we need to pick two irreducible SU2 representations, one for the left term and one for the right term. We already know there is exactly one irreducible SU2 representation per dimension. So we can label the Lorentz algebra representations by two integers m and n, which are the dimensions of the left and right representations respectively. We can also label these by the spin numbers jl and jr, which are equal to the dimensions -1 divided by 2. I also want to clarify the difference between the dimension of a Lie algebra and the dimension of a Lie algebra representation. The dimension of a Lie algebra is just the number of independent generators in the algebra. So SL2C is a 6-dimensional algebra because it has 6 generators, which act as the 6 basis vectors for the vector space. Similarly, SU2 is a 3-dimensional Lie algebra because it has 3 generators. The dimension of a representation, however, is the size of the matrices used in a matrix representation. So while the SL2C Lie algebra is always a 6-dimensional algebra, its matrix representations can have different dimensions, like 1, 2, 3, and so on. So this direct sum here indicates we are combining two sets of 3-dimensional Lie algebra generators into a space with 6 generators. Whereas this tensor product indicates we are taking the tensor product of representation matrices, thus multiplying the dimensions of the representation spaces. Okay, so let's start looking for matrix representations of the J rotation and K boost generators. We know the formulas for the A's and B's, and we can reverse these formulas to solve for J and K. If we have a matrix representation ρ of a rotation matrix generated by J, we can rewrite J in terms of A and B. Since A and B commute, we can split this into a product of exponentials. As we explained previously, we can write these commuting group members as an ordered pair, and the matrix representation can be written as a tensor product of a left representation ρl for the left group member and a right representation ρr for the right group member. To get the generator representation matrices, we take the derivative and set the parameter to 0. The derivative gives product rule over the tensor product, and after we set the parameter to 0, these terms become generators in the matrix representations denoted by pi, and these terms become identity matrices. We can get a similar formula for boosts, except the formula has a minus sign in the middle and is multiplied by an overall factor of -i. It's worth noting that, while the A's and B's live in the complexified SL2C Lie algebra because of the complex coefficients, the J's and K's live in the real version of SL2C, and coefficients are assumed to be real. So we have these formulas for the J and K generator matrix representations. We just need to pick SU2 irreps for pi L and pi R. We can say the left representation will have dimension m with spin jl, and the right representation will have dimension n with spin jr. So now the matrices on the left side of the tensor products have size m, and the matrices on the right side of the tensor products have size n. And the matrix representations of the J's and K's are denoted by two integers m and n. Alternatively, we can denote it by two spin values jl and jr. Now we can start exploring this table of irreps by choosing different combinations of dimensions m and n, or spin values jl and jr. The scalar representation is where the dimensions m and n are both equal to 1. In terms of the spins, both the left and right spin values are 0. The 1 by 1, or spin 0 representation of any SU2 matrix is the 1 by 1 matrix containing a 0. So for the m equals 1, n equals 1 representation of a rotation generator J, when we sub in our representation matrices, these 0 matrices make both terms in the sum go to 0. So we end up with just a 0 matrix. The same is true for the representations of the boost matrices. So for the m equals 1, n equals 1 representation of SL2C, all the generator matrices are 0. When we exponentiate these generator matrices to get matrices in the Lie group SL2C, we just get 1-by-1 identity matrices. What this means is that particles which transform under this representation are completely unchanged by rotations and boosts. These transformations are equivalent to just multiplying by 1. For this reason, objects that transform under this representation are called scalars. They look the same in all reference frames. Now let's look at the spin 1/2 representations. For SU2, the spin 1/2 irrep, also called the 2x2 irrep matrices, are given by -1/2 times pairs of Pauli matrices. Let's look at the m equals 2, n equals 1 irrep. In terms of spins, this is the 1/2, 0 irrep. For rotation matrices, since the second term in the sum is the 1-by-1 irrep, it goes to 0 and can be ignored. For the first term, we have our 2x2 irrep tensored with the 1-by-1 identity matrix. This tensor operation leaves the 2x2 matrix unchanged, so we're just left with our standard 2x2 irrep. For boosts, we get something similar, except there's a factor of -i in front of the matrix. So in this irrep, rotation generators are given by SU2, and boost generators are given by -i times SU2. We know SU2 generators are just -1/2 times pairs of sigma matrices. For boosts, we multiply by -i. But there's a property for the sigma matrices where if we multiply a pair of sigmas times -i, we just get the third sigma. So the boost matrices are just -1/2 times an individual sigma corresponding to the boost direction. So these are the generators for the m equals 2, n equals 1 irrep. And when we exponentiate them, we get these rotation and boost matrices. Particles that transform under this representation are called Weyl spinors, specifically left chiral Weyl spinors. Now, this is not the only spin 1/2 representation. We can also look at the m equals 1, n equals 2 irrep. In terms of spins, this is the 0, 1/2 irrep. If we look at the formula for the rotation generators, this time the first term in the sum goes to 0. Once again, we're left with an SU2 representation. This time we're representing the B generators instead of the A generators, but since the A's and B's both denote SU2 generators, this is still the 2x2 SU2 representation. However, with the boost formula, the first term goes to 0, and the second term contains a minus sign. This cancels with the minus sign out in front, and we get multiplication by +i. This has the opposite sign compared to what we saw for boosts in the left chiral representation. So in this irrep, rotation generators are given by SU2, and boost generators are given by +i times SU2. The generators and their Lorentz transformations look like this. These transform right chiral Weyl spinors. So we have two different spinor representations of the Lorentz group. The rotation generators are the same in both cases, but the boost generators have opposite signs. We call these the left chiral and right chiral spinor representations. Now, it's important to note that we cannot swap between the left and right chiral representations using a change of spinor basis. I proved this in video 9. So these two representations are not equivalent representations. The left and right chiral particles they transform are indeed different. However, we can swap between these two representations by changing the signs of all the sigmas. The rotation generators are unchanged since the two negative signs cancel, but the boost generators do change sign. So we can think of the left and right chiral representations as being related to each other by reflecting the universe in a three-dimensional mirror, where the x, y, z coordinates are all sent to their negative versions. The same rule applies to the SL2C Lie group matrices that we get by exponentiating the generators. The rotations are the same, but the boosts have their signs reversed. If we take the direct sum of the left and right spinor representations, the left and right chiral Weil spinors stack on top of each other and give us a Dirac spinor. Dirac spinors transform with 4x4 block diagonal matrices consisting of a left chiral SL2C block and a right chiral SL2C block. Also, if we take the four gamma matrices, written in the Weil or chiral basis, and multiply them all together along with the complex I, we get a new matrix which is normally called gamma 5. If we multiply gamma 5 by a Dirac spinor with only the left components non-zero, we get that same Dirac spinor times -1. And if we multiply gamma 5 by a Dirac spinor with only the right components non-zero, we get that same Dirac spinor times +1. So left and right Weil spinors are the -1 and +1 eigenspaces of the gamma 5 operator. We can also use gamma 5 to define the left and right projectors PL and PR. These projectors square to themselves and add to 1. They can project out the left and right components of a Dirac spinor, which can then be added together again to give the original Dirac spinor. Now, let's look at the m equals 2, n equals 2 representation. In terms of spins, this is the 1/2, 1/2 representation. This is the representation that transforms 4D spacetime vectors. When looking at the formulas for rotation generators, both the SU2 generators and the identity matrices are 2x2, and so their tensor products result in 4x4 matrices. The same is true for boost generators. Now, to get the actual group representation matrices that do Lorentz transformations, we need to exponentiate these generator matrices. Before I do that, I want to go over a few properties. If we have a formula of the form A tensor identity applied to identity tensor B, then by tensor product rules, we can apply first to first and second to second to get A tensor B. This also equals identity tensor B applied to A tensor identity, so the two terms commute with each other. Next, if we exponentiate A tensor identity, we get an infinite series in powers of A tensor identity. If we look at the squared term and do the application, we end up with A squared tensor identity. So really, the nth power of this expression is just A to the n tensor identity. This means that in our exponential series, we can move the exponent to the A, then use the tensor product rules to apply the scalars to the A, and also factor out the identity from the right in all terms in the sum. So we end up with an exponential series tensored with the identity, which means the whole thing is equal to e to the A tensor identity. We get a similar expression for the exponential of identity tensor B. Using these properties, we can now take the rotation generator representation formula and exponentiate it. We know these two terms in the sum commute, so we can rewrite it as a product of exponentials. Note that the tensor product rules require that we pass the scalar theta to only one term in the tensor product. Now we can apply the exponentials to the A and B representations. Then apply first to first and second to second, and we get this tensor product as the final result. We get a similar formula for boosts, except the signs in the exponentials are reversed. So given these SL2C algebra irrep formulas, we get these SL2C group irrep formulas. This shows the SL2C group irrep matrices can be factored into a tensor product of complexified SU2 matrices. So for our m equals 2, n equals 2 irrep of the SL2C group, we get a tensor product of left and right 2x2 complexified SU2s. Now, since complexifying the argument of an SU2 rotation matrix gives a boost, these two matrices are equivalent to left and right 2x2 SL2C matrices. So this tensor product property is a bit abstract. So let's look at how this works out with actual matrix components. We know the left spinor Lorentz algebra representation has these 6 matrices. The anti-Hermitian rotation generators give unitary rotation matrices, and the Hermitian boost generators give Hermitian boost matrices. The right spinor representation matrices are the same, but the boosts go in the opposite direction. In other words, these are the inverses of the left boost matrices. Now, if we take an SL2C matrix L, and take its Hermitian conjugate, then take its inverse, for the unitary rotation matrices, since the inverse is the Hermitian conjugate, the combination of Hermitian conjugate and inverse operations cancel out, and the matrix is unchanged. But for boost matrices, which are Hermitian, the Hermitian conjugate does nothing. So we're left with just the inverse, which reverses the boost direction. So if a matrix L belongs to the left spinor representation of SL2C, then the Hermitian conjugate inverse of L belongs to the right spinor representation of SL2C. Again, this operation leaves rotations the same, but reverses the boosts. Now, in video 9, I also introduced a kind of scalar product for Weyl spinors, which uses this epsilon matrix. This product is left unchanged by Lorentz transformations, which leads to the property that L transpose epsilon L equals epsilon. This can be rewritten in a number of ways. If we look at this scalar product, we can identify this psi as a left Weyl spinor, and identify psi transpose epsilon as a left dual Weyl spinor. If we complex conjugate this entire formula, we can identify psi transpose conjugate epsilon as a right Weyl spinor, and identify psi conjugate as a right dual Weyl spinor. So we previously talked about the left and right spinor representations. So where do these dual left and dual right spinors come from? It turns out these are not from new representations. We can flip between the left and left dual spinors by invoking the transpose and using epsilon as a change of spinor coordinates matrix. The same is true for changing between the right and right dual spinors. So the dual spinor representations are not new. They're ultimately just a change of coordinates from the spinor representations we already know. For matrices, the change of coordinates is done by using multiplication by epsilon and epsilon inverse on either side. So the left and left dual representations are equivalent, and the right and right dual representations are equivalent. Using the algebraic properties we've learned so far, we can deduce that taking a left chiral SL2C matrix L and complex conjugating it gives the corresponding right chiral dual SL2C matrix. This is a fact we'll keep in mind for later. Remember, we can rewrite a four-dimensional spacetime vector as a Weyl vector, which is Lorentz transformed using an SL2C matrix L on one side and L dagger on the other side. If we take this double-sided Lorentz transformation formula and churn through the matrix multiplications to get 4 equations, we can summarize all the coefficients using this 4x4 matrix. This 4x4 matrix is really just the tensor product of a left SL2C matrix L and its complex conjugate, which, remember, is the corresponding SL2C matrix from the dual right representation, which is equivalent to the right representation under a change of coordinates. Now, this 4D spacetime vector has all the components mixed together, but we can separate them using this change of coordinates matrix C. We can then take our 4x4 matrix and change coordinates using C and C inverse on either side to get a Lorentz matrix which transforms familiar 4D spacetime vectors. So when we tensor the left spinor and right spinor representations of SL2C together, we really do get a 4x4 Lorentz group representation which transforms 4D spacetime vectors. So the tensor product of the left spinor representation and the right spinor representation really does give us the vector representation. Now let's look at the m equals 3, n equals 1 representation. In terms of spins, this is the 1, 0 representation. The 3D representation of SU2 matrices is the same as the case of the generators for standard 3x3 rotation matrices. As we saw before, when one of the representations is 1 by 1, its term in the sum goes to 0, and the tensor product with the 1 by 1 identity doesn't change the result. So we end up with the standard 3x3 rotation generators. And for boosts, we just multiply them by -i. Now for the m equals 1, n equals 3 representation. In terms of spins, this is the 0, 1 representation. We get the exact same thing as before, except now it's the first term in the sum that goes to 0. And as a result, for the boosts, we get multiplication by +i instead. So once again, we've ended up with left and right representations where the rotations are the same, but the boosts are reversed with opposite signs. These are the left spin 1 representation and the right spin 1 representation. The 6 Lie algebra generators are 3x3 matrices, and they can be exponentiated into these 3x3 Lie group matrices. But what do these correspond to physically? Well, if we combine the two representations together using the direct sum, we get a 6-dimensional representation, which transforms the 6 components of the electromagnetic field, also called the Faraday tensor. Vectors in 4D spacetime have 4 components, but the electromagnetic field has 6 components. This is because the electromagnetic field is not a vector, it's a bivector. In 4D spacetime, there are 6 different ways we can group pairs of basis vectors together into bivectors. I'm going to use the Clifford algebra notation from videos 11 and 12 and denote basis vectors using the gammas, and basis bivectors using pairs of gammas. The bivectors that include one time direction and one space direction correspond to the electric field E, since the electric field can linearly accelerate charged particles, thereby giving it more energy and more momentum. The bivectors made of 2 space directions correspond to the magnetic field B, since they can cause a charged particle to circle using centripetal acceleration, which exchanges 2 of the momentum directions but doesn't change the energy. But how does this fit in with the 1, 0, sum 0, 1 Lorentz representation? If you recall, we previously used gamma 5 to separate a Dirac spinor into left and right halves. The left half had an eigenvalue of -1, and the right half had an eigenvalue of +1 under gamma 5. We can do something similar by applying gamma 5 to the electromagnetic field. Remember, squaring the gammas gives either +1 or -1, and swapping the order of 2 different gammas gives us a minus sign in front. If we apply gamma 5 to the gamma t, gamma z bivector, after swapping and computing the squares, we get I, gamma x, gamma y, which is another bivector. So gamma 5 has the effect of turning bivectors into other bivectors. Here's the action of gamma 5 on all the bivectors. Using these rules, we can build these 3 linear combinations of basis bivectors. When gamma 5 acts on these, it returns the same bivectors but with a -1 in front. In other words, these are eigenbivectors of gamma 5 with eigenvalues of -1. Now, if we take these three bivectors and reflect the spatial directions so that gammas x, y, and z become negative, we get another set of three bivectors. When we act on these bivectors with gamma 5, we get eigenvalues of +1 instead. Sometimes you'll see these bivectors multiplied by an overall factor of -1, but this doesn't change their eigenvalues. They still span the same +1 eigenspace. So we've divided the 6-dimensional space of spacetime bivectors into a pair of 3-dimensional subspaces, the -1 and +1 eigenspaces under gamma 5. And we get from one subspace to the other by mirroring the spatial dimensions x, y, z. We can also use the left and right projectors we defined previously to split the electromagnetic field tensor into left and right halves. It turns out that these -1 and +1 eigenspaces transform independently under Lorentz transformations. To prove this, we just need to show that the +1 and -1 eigenvalues are unchanged when we do a Lorentz transformation. Let's take a bivector alpha with eigenvalue +1. From video 12 on spin groups, we know that we can Lorentz transform this bivector using a double-sided exponential. Note that because we're in space-time, the left exponential has a plus sign and the right exponential has a minus sign. Recall that we can expand this exponential using Euler's formula to give a scalar cosine term and a bivector sine term. And we use hyperbolic trig functions if we're doing a boost. Now we want to apply gamma 5 to this Lorentz transformed version of alpha and show that the eigenvalue has not changed. This is easy to do because gamma 5 commutes with all bivectors in space-time. So we can slide gamma 5 past the exponential, have it act on alpha to give +1, then bring the +1 back out in front. So the Lorentz transformed version of alpha retains the same eigenvalue of +1. A similar proof can be shown for a bivector beta that has an eigenvalue of -1. So the +1 and -1 eigenspaces are indeed invariant under Lorentz transformations. The bivectors with eigenvalue -1 are called anti-self-dual bivectors. These transform with the 1, 0 Lorentz representation, and correspond to left circularly polarized electromagnetic waves. The bivectors with eigenvalue +1 are called self-dual bivectors. These transform with the 0, 1 Lorentz representation, and they correspond to right circularly polarized electromagnetic waves. So we can take our electromagnetic Faraday tensor and perform this change of basis to the eigenbivector basis. The components of F in the new bivector basis become complex linear combinations of the E and B fields. As we showed, each of these two eigenspaces transforms independently under Lorentz transformations. So we can transform this 6-component column using a 6x6 matrix, which is broken into 3x3 block diagonal sections. These 3x3 blocks are the 1, 0 and 0, 1 Lorentz representations. As an aside, this form of the electromagnetic field is called the Riemann-Silberstein vector. We can identify these two eigenspaces with left and right circularly polarized electromagnetic waves. The cross product of the E and B fields will always give the direction of electromagnetic wave propagation. So we can define left circular waves as having the B field lag behind the E field by a quarter phase with -I. And right circular waves will have the B field lead the E field by a quarter phase with +I. Looking back at our 6-component column, in the left circular case, only the top half is non-zero. And for the right circular case, only the bottom half is non-zero. So these really do represent the left and right circular polarizations of the electromagnetic field. You can pause if you want to look at the details, but this is how the anti-self-dual bivectors rotate. This is how they boost. And here is how the formulas line up with the representation matrices. It's also worth noting that the way we mixed the E and B fields to get a nice splitting into two parts is exactly the same mixing of the rotation and boost generators in the Lorentz algebra that we did to split the Lorentz algebra into two pieces. And the self-dual and anti-self-dual basis vectors we defined are algebraically equivalent to the A's and B's. And as another aside, the concept of self-dual and anti-self-dual bivectors is usually defined using the Hodge star operator in differential geometry. However, in space-time, the Hodge star gives imaginary eigenvalues, whereas gamma 5 gives real eigenvalues. So I used gamma 5 in this video to get real eigenvalues. Finally, we'll look at the m equals 3, n equals 3 representation. In terms of spins, this is the 1, 1 representation. Getting the generators involves the tensor product of a pair of 3 by 3 matrices, so we'll end up with 9 by 9 matrices. This is related to transforming rank 2 tensors in space-time. We're going to focus on covariant rank 2 space-time tensors, which have two lower indices. These take two vectors as input and produce a scalar. In array notation, the rank 2 tensor M is a 4 by 4 matrix, and the input vectors v transpose and w are sandwiched on either side. Now, if we Lorentz transform the vectors with a Lorentz matrix lambda inverse, then to ensure we get the same scalar result in the new reference frame, M must transform with lambda transpose and lambda on either side. M has 16 components, so it transforms under a 16-dimensional representation of the Lorentz group. This means we could choose to write M as a 16-component column and write the tensor product of lambdas as a 16 by 16 transformation matrix. Now, we can define the symmetric part of M as a matrix S, which equals M plus M transpose divided by 2. And we can define the antisymmetric part of M as M minus M transpose divided by 2. S is symmetric, so S transpose equals S. And A is antisymmetric, so A transpose equals negative A. And if we add S and A back together, we get M back. If we Lorentz transform the symmetric part S, the result is also symmetric. And if we Lorentz transform the antisymmetric part A, the result is also antisymmetric. So when we have a covariant rank 2 tensor in space-time, the 10 symmetric components and the 6 antisymmetric components transform independently from each other. So the 16-dimensional representation decomposes into the direct sum of 10 and 6-dimensional representations. Now, the 10-dimensional symmetric representation can be decomposed further, because the trace of a rank 2 tensor is invariant in all coordinate systems. Now, we have to be careful here. If we take the matrix for our rank 2 covariant tensor M, the sum of the diagonal elements is not invariant under a Lorentz transformation. Instead, we need to raise an index using the inverse metric tensor G. We're taking the metric G to be a covariant rank 2 tensor, so it Lorentz transforms like this. We're also assuming it's invariant under Lorentz transformations, so G equals the Lorentz transformed version of G. And that leads to this property. After we apply G inverse to M, this raises an index and we get a 1 contravariant, 1 covariant version of M. Now when we sum the diagonal elements, we get the invariant trace of M. This version of M transforms with lambda inverse on the left instead of lambda transpose. And this is what makes the trace invariant under Lorentz transformations. I'm going to define the matrix T to be the identity matrix times the trace of M over 4. Basically, the 4 diagonal elements each hold a quarter of the trace of M. and so their sum gives the trace of M. So the trace of T equals the trace of M. Since both the trace and the identity matrix are unchanged by Lorentz transformations, this T matrix is also unchanged by Lorentz transformations, and so T acts like a scalar. We can get the covariant version of T by applying the metric g to it to lower one of its indices. Using the properties of the metric, we now see this new GT matrix is invariant under Lorentz transformations for covariant rank 2 matrices. So this GT matrix behaves like a scalar. So the 10-dimensional symmetric representation S further breaks down into a one-dimensional trace part given by GT and a 9-dimensional symmetric traceless part given by S minus GT. The 9-dimensional part is the irrep transformed by the 1,1 irreducible Lorentz representation. So to sum up, a rank 2 covariant tensor M has 16 components. This breaks up into the direct sum of several sub-representations: the 9-component symmetric traceless part, the 6-component antisymmetric part, and the 1-component trace part. Rank 2 tensors can be thought of as tensor products of pairs of rank 1 vectors. So in space-time, M lives in the representation space of the tensor product of two 1/2, 1/2 irreps, which are the vector irreps. This decomposes into the direct sum of several irreps. The 1-component trace part is the 0, 0 scalar irrep. The 9-component traceless symmetric part is the 1, 1 irrep. And the 6-component antisymmetric part is given by the 1, 0, some 0, 1 representation, which is exactly what we saw for the electromagnetic tensor, which is also an antisymmetric rank 2 tensor in spacetime. So to sum up this video, we learned that if we took the 6 generators of the SL2C Lie algebra and changed basis to the A's and B's using complex coefficients, we could decompose the complexified SL2C Lie algebra into 2 copies of the complexified SU2 algebras. And this means elements of the SL2C Lie group can be decomposed into pairs of elements from the complexified SU2 Lie groups. So to understand the irreducible representations of the SL2C Lie group and Lie algebra, we just need to pick 2 irreducible representations of the SU2 Lie group and Lie algebra, and take their tensor product. The 2 irreducible SU2 representations can either be identified by their dimensions m and n, or their spin values j left and j right. By picking different values for these spin numbers, we can write out all the irreducible representations of SL2C using a 2-dimensional table. Irreps in the first column are called left representations, and irreps in the first row are called right representations. We can flip back and forth between left and right representations just by reversing the spatial x, y, z directions using minus signs. We can also identify left and right representations using the eigenvalues of the gamma 5 operator, and project out left and right sub-representations using the left and right projectors.